So now we will move on to the geometric distribution. This is also discrete. But it's a bit more, it's got almost the same criteria, the same conditions as a binomial distribution, except for one. No fixed number of trials. It's still discrete because the probability of an exact value isn't 0. But the rest, it still has to have independent trials, fixed probability of success, only success fail, so only 2 outcomes. And basically the idea of a geometric distribution is you keep trialing until you succeed, and then you stop. A common example might be like trying to find a ball date or something. You ask people, you get turned down by the first question, then you'll just keep asking until you actually get someone. And then when you do have someone accept your request, it's not like you're going to go and keep asking people, right? You'll stop once you've succeeded once. So let's think about that a little bit. If we have P, probability of success, and we'll keep asking people until we get that first P. So the probability, let's call it X again, equals lowercase x, will equal P, and then we'll account for the number of failures, 1 minus P, and it'll be n minus 1 times, right? Well, in this case it'd be x minus 1 times, because we've used the x here. Because say, the first person you asked a ball says yes, then you've done that P, but then you've failed no times, but you've done 1 trial, and 0 is 1 minus 1. But then say you had to ask 10 people, the 10th person you asked said yes, that means 9 people said no, which is x minus 1. And if you remember how we did x, b, n, p, something like this, because there is no fixed number of trials, for geo there's no n, so it would be x, and for some reason we do geo, and then it would just be the p is the only parameter. So obviously something you might get in the exam is, okay, the probability of John scoring a basketball shot during practice is 0.5. And he takes a break after the first shot he makes. What's the probability that he takes a break after the 8th shot? And then you just do 0.5 times 8 minus 1, and something like that, right? But sometimes it might ask, what's the probability that x is less than x. And if it's less than, because it's discrete, I would then convert that into x minus 1. Make it an equals. Something like that. But if we just ignore that minus 1 and just talk about px is less than x, let's take an example. Px is less than 9, and we'll say that it's a geometric distribution with probability 0.3. And this is basically saying px equals 0 plus px equals 1 plus px equals 2, and on and so forth. And we know that px equals 0, well, you can't have that. You can't have 0 trials. Good life advice. You won't have any success if you don't try at least once. So, and then this, as we know, would be p, and then this would be p1 minus p, and then this would be 1 minus p squared, and hopefully you're starting to see that this is called geometric for a reason. It forms a geometric sequence. So then this just becomes, because we're going all the way up to p1 minus p to the power of 8, this becomes a sum of the first 9 terms, which is a 1 minus r to the power of n. A is first term, r is common ratio, 1 minus r. So that's p, 1 minus p to the power of n over 1 minus p. And if we have a look at this, that becomes 0 and that becomes p. So those p's cancel out. So then we just get 1 minus p to the power of n. So that's why px is... I've completely ignored the example values that we've done, but that's fine. We can say that px is less than or equal to x is 1 minus p to the power of n. On the other hand, if we did greater than 9, I would keep it as a greater than 9, because what this is saying is we are looking for the probability that he has to try at least 10 times. And if he has to try at least 10 times, that means he has to fail at least 9 times. And as we know, if we look at a tree again, we stop at the end of a success, right? So then it'll just look like this. So if we want to go something greater, this way, all we need to do is just do a bit of multiplying of fail probabilities. So that's why this would be equal to 1 minus p to the power of 9. So px is greater than little x would be 1 minus p to the power of x. If you got greater or equal to, just change it to a greater than, so you don't make a mistake. And now let's move on to some expectations and variances and stuff. And on another note, what is the probability that he'll have success? So this guy shooting his shot in basketball, what's the probability that he will eventually have some success? Well, let's think about it. We're doing U1 plus U2 plus U3, and these are like terms, I'm saying, plus U4 and all the way up to U infinity, right? Well, this is looking like a sum to infinity. Well, that's A over 1 minus R. And so A is the individual probability, and then R is 1 minus P, right? As a common ratio. So we get P over 1 minus 1 is 0, but 1 minus p is, or 1 plus p, so it's just p over p, which is 1. So it's certain that if we try infinite number of times, we'll have success. Very inspirational, I know. And now the next thing we're going to go into is 3 things. The mode, the expectation, or the mean, and then that's it. We're not going to do the variance. The mode, always 1. I mean, that's obvious. Really, that's obvious. It should be so obvious. You're only doing p. As any point after that, you're doing p1 minus p. And this is always a between 0 and 1, so it's only going to make it smaller. So the mode will be 1. And on a graph, it looks like this. An exponential decay curve. So 1's always going to be the highest probability. And then the expectation. Well, think about it. Say your chances, you know how they say 1 in 4 people have diabetes? So if you were to go around and ask and find out if someone has diabetes, how many times would you expect to have to ask people to find at least one person with diabetes? Well, if it says 1 in 4, I'm making up numbers, by the way, you would probably expect to do it, have to go around 4 times, right? So that means our expectation is 1 over p. Because 1 over 1/4 is just 1 times 4 over 1, which is 4, right? So yeah. So all in all, that is it for geometric distribution and discrete random variables.